Hello, and welcome back to the Molpigs podcast. Today we are following up with Brenda Rubenstein's tutorial on her lab's work in storage and computing with small molecules. If you haven't seen it yet, make sure you do now, as it really is fascinating. Also with me today are Anastasia.
Hello.
Boya.
Hello.
And I'm Will. Brenda is currently the Joukowsky Family Assistant Professor of Chemistry at Brown University. While the focus of her work is on developing new electronic structure methods, she is also deeply engaged in rethinking computing architectures. Prior to arriving at Brown, she was a Lawrence Distinguished Postdoctoral Fellow at Lawrence Livermore National Laboratory. She received her SCBs in Chemical Physics and Applied Mathematics at Brown University, her MPhil in Computational Chemistry whilst a Churchill Scholar at the University of Cambridge, and her PhD in Chemical Physics at Columbia University. Brenda, hi.
Hi, Will. Thank you for inviting me, and thank you for organizing this.
Thanks for joining us. We've got a lot of questions here, so we might not be able to get through them all, but how about we start with one from you, Boya?
I have a very naive question. Why do you need to synthesize the eugene molecules if the information is stored in the combinatorics of the reaction substrate? And I assume that HPLC can help read out what the substrates are.
Mm-hmm. So you're absolutely right. When we first started this project, we were trying to look for one synthetic chemistry that could cover everything. We increasingly realized that you don't need any of that. So you're absolutely right. So as long as you can assemble a collection of molecules that have distinct mass spectral patterns, then you're all good in our scheme. And so we have been using things like metabolites. We've also been using things like just regular phenols because they're cheap to get. But your point definitely drives home the message. We could use things like peptides that we can get off the shelf. We also thought about ordering large libraries of molecules from various companies, and we can use those as well. So you're 100% right. In our methods, very general across different types of and classes of molecules.
I have a very big picture of a question. So, in order for information storage and processing molecules to be more widely available, say on a global scale, or we would ideally need to see a pretty big shift in everyday technology and how we do things, or at least some sort of way of seamlessly interfacing with today's computers. How do you foresee these issues being overcome, and what time scale do you think we're looking at for this?
Mm-hmm. Yeah, this is a very important question. I don't think this is something that's going to happen overnight, but my view of it is that silicon does a lot of things incredibly well. But there are things that silicon doesn't do well, and it's exactly what you're talking about, is basically interfacing with chemistry and biology. So if you think about the way chemistry and biology works, right, it's basically entirely controlled by molecules. And so whenever you have to interface silicon with biotechnology or with chemistry, then you have to find a way to actually translate information from silicon to the molecules and back and forth. And that can require a lot of overhead. And so what we really need to work on is that interface. And the big picture that at least I foresee is that these kinds of technologies, whether they be DNA or they be small molecules, are trying to go basically beyond the current computing paradigm to try to fill in things that, let's just say, at the border that silicon just doesn't do particularly well right now. So I think in order to realize those advantages, we really have to work at that interface, and I think there are a lot of issues and problems at that interface. We would have to be able to actually design ways of silicon technologies to recognize molecules quickly and rapidly on very, very small scales, to be able to analyze them, to be able to detect them, and also be able to actually pass signals to them. And of course, people are trying to work at that interface, but I don't think it's quite there yet. So I think the big picture is, we're trying to fill in one area where, obviously organisms and biology computes with these kinds of molecules, but we need to bring the two areas together for molecules to really make sense as a technology moving forward.
And it seems like there's a lot more work going on right now on the side of just figuring out how to do things in molecules as opposed to working on the interface. So do you think it's on us in academia to figure out that interface and then convince the tech industry hey, we actually have a working solution, or just tell them hey, we have this really cool approach with molecules, go figure out how to integrate that with everything else?
Yeah, I don't know if it's specific to your question, but I think is it our responsibility? I wouldn't quite phrase it that way, but I do think that academics are the ones who put forth the ideas in sort of the way I think about it is sort of stepping stones. We put down those stepping stones so that other people in industry and elsewhere in academia can actually build around those stepping stones. So I do think that we have to lay some of those foundations and do a better job there. I don't think it's entirely our responsibility to do that, but I still think the key ideas have to be built there, and then we can go in and say, amazing engineers, come on and go ahead and engineer this.
Another question I have is, by listening to your tutorial, I'm wondering about the last part. The last part you mentioned that the current existing theories for creating computing using chemistry is not practical. So I wonder, can you elaborate on that? What do you mean by they're not practical, and what kind of computation is that?
Okay, sure. I'm not trying to be offensive to anyone, but I think there are a lot of theories out there that do not work with practical small molecule chemistry. So a lot of those theories were originally developed with DNA in mind. DNA has the benefit of the fact that it hybridizes quite cleanly. So yes, you can get strangely hybridized structures, but essentially in DNA, if you build your sequence into your strands, you can to some degree control your hybridization. That's a really nice benefit of DNA. Most of chemistry does not have that ability. So if you take arbitrary reactions and you propose them, they're not going to work for real chemistry. And so we faced this issue many times. You can't just tune your rate constants to whatever you want. You can't create series. So if you're talking about computation that requires 20 different reactions to complete and also doesn't take into account side products that are produced along the way, that's not realistic for everyday chemistry. And so that's a little bit of what I'm getting at. I think a lot of the theory was created with DNA in mind, but DNA is an exception. It's not the rule in chemistry.
So is there any other ways to not, so those theories you mentioned are mainly DNA. Is there any more chemistry-related theory about computing that currently existing?
No. No, as far as I'm concerned. So there are a lot of demonstrations done by forward-thinking chemists about how information can be stored and a little bit about how things can be processed, mostly in non-equilibrium reactions. But there's no real theory for any of it. And so I think this is a very large open area of really making a theory that matches chemistries that really go on in the everyday lab. And so we're trying to think about those theories quite deeply right now, but there's a lot of opportunity to do better.
And just to dive into the comparison with DNA a little bit more, so like this sort of programmability and the ability to tune like DNA reactions is definitely a strength of like DNA computing. Do you think it is an Achilles heel for chemical computing that we need to overcome, given that there are sort of other entities like DNA that don't have that problem?
So I think we have to think about problem spaces. So I think DNA has a clear strength in the fact that it's so programmable. With respect to small molecules can basically actuate. They can represent other types of functions that DNA is not. It's not so easy to program into DNA. So for example, you can create very, very complex sets of large series of coupled differential equations that you can represent using these different reactions, and the rate constants can vary. And you can also talk about not just having two molecules react at a time. You can have series of molecules react in very complex ways. So the advantage for small molecules is that there are more different types of computing that are possible, but it's definitely not going to be as specific. So yes, there's a little bit of an Achilles heel, but there's also a little bit of a trade-off in terms of what are the kinds of functions that you may be able to create.
So in that sense, do you envision that like, DNA and small molecules could coexist within one computing system?
I do think so, and of course, it's what happens in biology. So I am absolutely motivated by that comparison. We have small molecules in our bodies that are orchestrating a whole bunch of different things, not even molecules, ions, that are orchestrating things and constantly interacting with our DNA. So I'm very hopeful that we can, build even more capacious storage paradigms that use both, but also to create interesting computing paradigms that use both.
So in this sort of biology analogy, we can see that DNA tends to be very long lasting and it doesn't really get degraded in a cell, but small molecules are constantly being renewed. But in terms of long-term data storage and computing, maybe one would argue that that sort of framework is not super appropriate, and DNA is quite robust in the sense that we've been able to sequence several thousand-year-old DNA. Well, even though some of it might have been a bit degraded. But how resilient are, say, like the Ugi molecules been working for long-term data storage? Do you think that's a benchmark that other chemical storage modalities would have to match?
Yeah, so we've looked at our UGIs with respect to this, and the simple answer is we haven't found that they degrade at all. The reason why, under normal conditions, the reason being is that unlike with DNA, where you have lots of biological enzymes that are just around and could potentially get into a vial or a flask if you're not careful, there are no such enzymes for these kinds of molecules. So there's nothing natural that is going to break many of these species apart. And so maybe this ties back to Boya's question about why use certain types of molecules. We use the UGIs because they're super stable. There's nothing that's going to get them out of that free energy well in an easy fashion, whereas other types of molecules, that's not true. And so for us, we think that our molecules would be as stable as DNA. Of course, we can't go back and look for the caveman that had an UGI molecule in him and figure out how long it lasted. But there's no reason to believe, and we also haven't found in the lab, that we'd be suffering from degradation that would be any faster than would go on the DNA.
That's really interesting. And so do you also not see any degradation modalities like tautomerization, and are they quite resistant to UV radiation, that sort of thing?
Yeah, we haven't done the UV experiment. The UV might cause a problem, as it would for almost every molecule I can think of. But we also build our molecules so that if they tautomerize, it's not a particularly big deal in the way that we read things out. We haven't looked at everything, and I wouldn't guarantee you that if you bombarded our molecules with radiation that they would sustain that, but DNA probably wouldn't either. So I think we're still quite comparable.
Yeah, in that case, you can get away with just putting them in different physical encasings to protect them from radiation, which should not be a difficult challenge. But in that sense, sort of what spatial density of information storage can you achieve? Because right now it seems like you're limited by how small you can make the wells in a multi-well plate. And I was just wondering how that compares to other storage media as well, potentially.
Mm-hmm, mm-hmm. Yeah, so the use of the multi-well plates is really because of the fact that we want to do as simplistic and straightforward mass spectrometry or detection as easy as possible. But there's no reason that we couldn't just create one pot as long as we can read it out. So the plates were really just to make sure that we could very quickly read out subsets of our information. If we were to put everything in one pot, in one well, then according to our estimates, if we were using UGI molecules, again, we don't have to stick to UGIs, we're talking about 2 to 3 times as dense as DNA would typically be. So it's in the same ballpark as DNA, a little bit more dense because the molecules are smaller, but that's assuming that you can throw everything into one pot and then read it out. But my understanding, and maybe you can correct me if I'm wrong, from my engineering colleagues, is that also you can't immediately read out thousands and thousands of strands of DNA either, and so there is, in some sense, some segregation because you just can't read everything constantly through let's say a nanopore sequencer.
Following on from that, so some of the problems I think you went into is that it depends on how much monomer diversity you can get. So if you can't get enough diversity with your molecule of choice, then that limits the size of the pot you can do. Have you thought about any ways around that, such as localization, maybe having some kind of molecular lattice in order to get by with less diversity?
Yeah, we have thought about that, but I think the interesting problem, and please tell me if I'm wrong here, is just how do you really synthesize such lattices? So we can, wells are sort of an easy answer. We just use a physical substrate. But sort of starting from scratch, making sure that molecules separate into different places is a difficult thing synthetically. So we've thought about things like droplet compartments, or maybe even using different types of phase segregation to separate molecules. But if you just go into chemistry and ask chemistry to do that for you, it's really not easy, and it's actually an interesting frontier to figure out how to do that well, beyond maybe, let's say, 2 phases or 3 phases. And so we'd love to see that, but we haven't seen it yet, and that's why we haven't spent as much time there.
Related to that, have you thought about like some solid state chemical modalities, and maybe if we can do solid state molecular computing?
Can you define a little bit more what you mean by solid state here?
So, like in this case, we're for both DNA and for, I guess, the uji molecules, you kind of need to have them in solution, and so you're dealing with solutions. But maybe like in terms of thinking about interfacing with like everyday, like our phones or our computers, we'd probably want it to be solid, not liquid. So even just that in that very basic framework, are there any chemical modalities you envision would work in that way?
Yeah, I thought a little bit about this issue. I think mostly what one would be talking about is how would you store information on a surface, because if we're interfacing with solid state, we have to be essentially coding the molecules to a solid state structure. And yes, you can certainly pattern molecules. So if you're still storing information in the presence or absence of a molecule, you can imagine basically patterning a surface with molecules that prescribe what is the information at different positions. So I feel like we're mostly there with those kinds of technologies. In terms of storage, I think that's quite doable. I think what I still haven't figured out is how do you then compute having the molecules at a surface. It's a little bit trickier for me. But yes, I can certainly imagine having molecules tethered or just physi-absorbed or chemi-absorbed in different ways to a surface and using that interface.
Do you think that will be necessary going forward, or do you think people would be more open to, like, if we couldn't figure out how to do computing tethered to a surface, or do you think the community will be more open to doing it not on a surface?
Would be more open to doing it. I think what we have to prove first is that this really is a promising path. So I'm not even there to figuring out if the community will accept it in complement to solid state devices yet. I think we really have to say that molecular computing is its own niche. It's solving these classes of problems that really couldn't be solved in silico, and then we have to get to the point of figuring out how to interface the two. I'm not sure that we fully won that battle yet. I think we won storage. I'm not sure that we won computing yet.
But for computing, could you argue that maybe the biggest application would be speeding up reading and writing of things stored in molecules?
Mm-hmm. Yeah, you can certainly argue that. I think that's fair. I think that's absolutely fair. I guess I keep craving for something a little bit deeper than that. Trying to do something much more general than that. But we'll see where things go.
Regarding reading out the result, my knowledge for mass spec is pretty old. I'm not sure if they're advanced technology. For mass spec, do you need the molecules to be pretty pure to get a clean result? That means you will need to purify or separate the molecules to make sure they're pretty pure to get a clean mass spec, or you can do mass spec on them in parallel.
Mm-hmm. No, we don't have to purify anything. In fact, when we first started this project, we thought we would, but as it turns out, as long as we have reactions, as long as we can be sure that some percentage of the reaction is going on, we can see those products, and we can see those products amidst a whole other set of products. So our spectra are very, very messy, but what we're able to do is basically machine learn the features of the molecules that we hope to see, and so we can get around a lot of that noise. Now, if we weren't sure which reactions were happening with thousands or tens of thousands of molecules, yeah, we'd be in trouble because we'd have a really high noise floor for our mass spec. But in general, no, we haven't had issues with that. In fact, our reactions by synthetic chemist standards are super messy. We literally just throw our reactants together and they react, and some things react and some things don't react. So no, we're not doing any purification right now, but that's a good question.
So I can see how that's not a problem as for storage, but in terms of doing computations and error rates within computing, do you think that could be a limiting factor, or do you have to have like a lot of redundancy to overcome the messiness?
Yeah. So there are different ways of doing error correction, and so some of the techniques that we've had are things like sparsity. So if you're able to actually use reactions that move you between one state to another, between a couple of states that are well resolved from other states, we can get around some of these issues without necessarily having redundancy. And so that's one trick to doing some things. Now, do I agree with you overall? Yes, I do. So with computing, we will have to be careful about things like cross-reactivity, or we will have to basically say, the answers that we get from cross-reactions are just so different than the answers that we're looking for that we never even pay attention to that space. So there are some tricks if you can expect what's coming out.
Do you think that it is the case that you can expect what's coming out and then you can factor that into your analysis?
I think you can have a general notion of what's coming out. So if you're talking about all-purpose computing where we can put in, I don't know, if we're multiplying, any two numbers and then figure out what's coming out, that's where it would get very difficult. But at this point, I don't think we're talking about all-purpose computing where you're putting in any combination of inputs whatsoever. I think we're still sort of at the stage of we have some expectations of the kinds of things that are going to come out of our computation.
If I understand correctly, so your current experiments with computation are maybe it's fair to say at kind of the same stage as when, well, a bit further on, but when Len Edelman was working on Hamiltonian on the traveling sales problem, and where he was kind of manually doing each step of the reaction. So if I understood your slides, you were kind of manually pipetting between wells. Do you see a route forward to automating small molecule computation with maybe in a single pot?
We're all automated. So when we first started and didn't have the equipment, we weren't. But we are currently all automated for almost everything that we do. Now it's not fully single pot because of some of the analytical issues that I was describing. But that's for storage. For computation so far, we have been doing everything single pot basically.
Sorry for misunderstanding that. And going back to the storage you were mentioning, so mass spec machines can be pretty expensive, but obviously a lot of universities have them, so that's not as big of an issue. But do you maybe see any viable cheap alternatives coming around? How difficult would it be, for example, to amend an Oxford nanopore system to use it? Because that also uses machine learning on messy traces.
Yep. Yeah, we're thinking exactly about that right now. So we're thinking about how do we miniaturize our mass spec and how do we potentially use nanopore sequencing. One of the issues right now, and maybe you know more than me, but one of the things that we've been thinking about is just if you're talking about small molecules, how well can a nanopore do? So they have to have some reasonable extent for the nanopore to do well. But I think there's room for the technologies to grow there, and so we're thinking about how do we push that. And I think there is a lot of space to make smaller mass spec facilities available. Now, what I should say is just that we used a very large instrument. It turned out that we probably didn't need that. Maybe I shouldn't say that. Our funders might get upset, but we didn't realize it from the beginning. We thought we would really need a huge instrument, but using different types of error correction, using sparsity, we were able to get away with a lot smaller mixtures than we thought to achieve the same kinds of information densities. So actually, you could use your run-of-the-mill mass spec on many of the things that we're doing.
Yeah, this might be a very naive question, but do you lose a significant amount of sample every time you mass spec it to do your readings?
Yeah, so you're right. It is a destructive technique. We've thought about non-destructive optical techniques for reading things out. Depends upon the how many bits you're really storing and working with. Mass spec is nice because of the fact that you really can read a super large mass range, and the resolution of the peaks is good. Whereas a lot of optical technologies at room temperature, your spectra just have these broad peaks, and so it becomes a mess. So we definitely have thought about that. There's one person on our team who thinks about this all the time. He's our optics person. So we've thought about doing multimodal types of Raman, multimodal types of IR. They're still not going to give you quite the resolution that mass spec will, but there are other options for making things non-destructive.
And I guess DNA storage is destructive too when you read it. I guess what DNA does have is polymerase chain reaction. Obviously, for general molecules, it's a very difficult problem to think about copying them arbitrarily. Are UGIs in any way suitable for that, or can you think of any other small molecules that might allow you to copy chemically?
Yeah, so PCR is pretty unique, and obviously, if it weren't so unique, it wouldn't be so popular. So I don't know of any technologies that do that off the bat. Obviously, some people have come up with technologies that couple small molecules to DNA and then PCR up the DNA. Obviously, small molecules can also undergo autocatalytic reactions, and so there's some potential there, but there aren't that many autocatalytic reactions where you're talking about every molecule could potentially be amplified. There are certain paths, but we're not in the same place that PCR is.
So how easy is the synthesis then? So say if you were to read out a sample by mass spec and then you just wanted to make sure you constantly have the supply of it, can you use the mass spec signal to just synthesize more of the same thing?
You could, yeah, absolutely. So like I was saying, our synthesis is fully automated and we don't need the kinds of purities that most chemists are used to. So absolutely, you can synthesize basically on demand.
And have you looked at any kind of analog storage with your small molecule systems?
That's interesting. We thought about it, but the scaling for analog is not what you would expect. So when you're talking about, let's say, giving molecules multiple concentrations, so say you have 10 concentrations for each molecule that could be present or absent, then you're only getting essentially log base 2 of 10 of more possibilities there. And so it's actually not that much unless you're starting to talk about thousands, millions of concentrations, which wouldn't really be possible with many technologies right now. So yes, we've thought about analog. We just decided that it doesn't necessarily give you as much as you might hope.
Is there a way of incorporating more inorganic type chemistry within molecular chemical storage? Maybe that would even make reading out things in a non-mass spec fashion easier?
Yep. Yeah, we have. We just think that some of the synthesis is a little bit more challenging, but we haven't. Our synthetic chemist is actually an inorganic chemist, so we constantly think about, can we use redox reactions? And so the answer is yes, we could use those technologies. We just haven't gone down that path, in part because of the synthesis, and in part originally we wanted to create molecules that had sort of a combinatorial scaling of the number of combinations. We couldn't think of particularly good ways of doing that inorganically, but it's not to say that they don't exist out there.
And going back to the computation, would you say that perceptrons are a more natural computation for chemistry to do than maybe other computations? And could you maybe expand more on your thoughts at the end about overarching theories for chemical computation? Do you think that it's possible maybe to get a grand unified theory, whatever that might look like, or do you think we'll look at specific chemistries like what these organic molecules can do and what maybe in the future these inorganic molecules can do, rather than kind of a grand overarching one?
Mm-hmm, mm-hmm. Yeah. So we're always going to be bound by some of the specific parameters of chemistries. So for example, what their reaction order is, what their rate constants are, and so that's where the specific comes in. I think what people have to think of much more broadly is if you have a couple series of ordinary differential equations or even partial differential equations that represent what different reactions are doing. What are the kinds of computations you can get out of that and how can we control these systems, and can we control these systems to yield computations that we want. So there have been examples, again, by synthetic chemists, but I don't feel people have really worked intensively on this. There's some papers that have come out by the Microsoft group, their molecular computing group recently that are coming close to this, but I don't see, people aren't really thinking down that path as much as I think they should. The reason why I was talking about perceptrons are sort of a subclass of that larger class of just coupled reactions. The perceptrons, they multiply, accumulate like chemicals do naturally. They threshold like molecules do naturally. And of course, we see some of this in our own bodies. So I think there's something to be said that's sort of closer than gates for small molecule computing. I won't argue that for DNA, but for small molecule computing, I don't see a lot of great paths to making gates work yet. Yes, people have made single gates, but cascading them is not going to be so easy. What I'm trying to say is that there are things that are closer to the chemistry, and there are motifs that are further from the chemistry. And I think we have to build on some of the motifs that are closer to what the molecules are actually doing to create some understanding of what they can truly be capable of.
In terms of applications, how suited do you think small molecule computing could be for things like interfacing with biomarkers for diagnostics, or maybe even in vivo computation for maybe monitoring biology?
Yeah, so that's the application that we foresee, and that we think we're trying to constantly work towards. So you can imagine using small molecules to essentially modify maybe biopolymers or modify metabolic networks in different ways, because all of those things are already molecular, and so we can program small molecules to then interface with them and then sort of engineer those different systems. So that's absolutely the application. I think that is one of the key applications. There's some other applications out there that we've been thinking of. So one possibility is steganography. Other possibilities are also with soft robotics. So soft robots are essentially, I'll call them molecular, but they're materials based. And so you can imagine using small molecules to interface with those materials rather than electronics.
And could you maybe leverage isotopic differences in your R groups to increase information density?
Yep, absolutely. Absolutely. We just haven't done it. But this is definitely something that we've thought about.
I have a really serious question. Do you refer to failed oogie molecule experiments as oogie boogies?
Maybe we'll have to take that one. I haven't, but we'll credit it to you and go forth from there. See if we can get it into a paper.
Thank you, Brenda, for both your tutorial and for joining us today to answer some of our questions. It's exciting to see all the different avenues being taken in our field, and I can't wait to see where you and your lab go next. We'll be back in 2 weeks to speak with Dominic Scalise. Thank you for listening.